Today we can discuss isomerism. There are two types of isomerism in organic compounds. First one is structural isomerism and the second one is stereoisomerism. Now what is isomerism? Isomerism is a phenomenon in which there are molecules with the same molecular formula but different properties. In organic chemistry or in organic compounds, we can identify molecules with the same molecular formula, but they possess different properties. It may be due to the difference in the arrangements of groups or groups or atoms within the molecule, or it may be due to the difference in the spatial arrangement of atoms or groups. If the difference in the arrangements of atoms or molecules within the group, we will call it as structural isomerism. Isomerism arises due to the difference in the arrangement of groups or atoms within the molecule, that is structural isomerism. And stereoisomerism arises due to the difference in the spatial arrangement of atoms or groups in the molecule. That is stereoisomerism. Stereoisomerism, there are two types, geometrical isomerism and optical isomerism. We will discuss geometrical isomerism in the next chapter and optical isomerism in the second year topic. Now we can concentrate the structural isomerism, concentrate two structural isomerism. First one is chain isomerism. It is classified into four. First one is chain isomerism, second position isomerism, functional group isomerism, and metamerism. What is chain isomerism? In chain isomerism, the molecules have same molecular formula, but they differ in the number of carbon atoms in the longest chain. Or we can say they differ in carbon skeletons. When two or more compounds have similar molecular formula but different carbon skeletons, these are referred to as chain isomers. The number of carbon atoms in the longest chain will be different. Here you can see three examples: pentane, 2-methyl-butane, 2,2-dimethyl propane. So it is pentane, longest chain contains 5 carbon atoms. This 2-methyl-butane contains 4 carbon atoms, longest chain contains 4 carbon atoms. 2,2-dimethyl propane contains 3 carbon, longest chain contains 3 carbon atoms. Here, 2 of the carbon atoms are present as side chains or substituents. Here, 1 carbon atom is present as substituent. But if you check the molecular formula of these compounds, you can see all of them have the same molecular formula, and that is C5H12. C5H12. So it is chain isomerism. You can identify or you can write examples for many other chain isomers. Now position isomerism. Position isomerism arises due to the difference in the position of functional group or multiple bond. So position isomers, they have general molecular formula, but they differ in the position of functional group in the molecule. Only in the position of functional group or only in the position of double bond or triple bond. That is the only difference. An example, but2-ene and but1-ene. In but1-ene, double bond is starting from the first carbon atom, and in but2-ene, the double bond is starting from the second carbon atom. The position of double bond is different. Therefore, but1-ene and but2-ene are position isomers. Another example is this one, propan-1-ol and propan-2-ol. What is the difference between this molecule? Only in the position of OH group. In the first compound, OH is attached to the carbon, first carbon, and in the second compound, OH group is attached to the second carbon. Now the third one, functional group isomerism. Same molecular formula, but they differ in functional group. The functional group present in the 2 molecules or 2 or 3 molecules will be different. That is functional group isomerism or functional isomerism. 2 or more compounds having the same molecular formula but different functional groups are called functional isomers. Here you can see an example, propanol and propanol. Propanol is a ketone. Propanol is an aldehyde. So ketones and aldehydes are functional group isomers. We can identify another such a group, another such a pair. Ethers and alcohols are functional group isomers. For example, dimethyl ether, methoxymethane and ethanol. Another example for functional group isomers. And the last one is metamerism. It arises due to different number of carbon atoms on either side of the functional group. In the case of ethers, we know divalent oxygen is the functional group. So on either side of the functional group, there are different alkyl groups. So the metamers, these metamers differ in the number of carbon atoms on either side of the functional group. Their molecular formulas are the same. An example is given here, C4H10O, that is the molecular formula. And the first compound, methoxypropane, CH3O, C3H7, and the second compound, ethoxyethane, C2H5O, C2H5. From the molecular formula, it is very clear that these two compounds are different, isn't it? It is different, but their molecular formulas are same. What is the difference between these two compounds? Here 1 and 3 are the number of carbon atoms on either side of the functional group, but here 2 and 2 are the number of carbon atoms on either side of the functional group. It is isomerism. Now you have a question, write all the possible isomers of C4H8. C4H8 means CnH2n. It is the general molecular formula of an alkene. So 4 carbon atoms, so but, 1 in, but, 2 in. 2 possible, 2 position isomers. Now chain isomers, also possible. 2-methyl propene, that will be the chain isomer. One more isomer is possible, that is cyclobutane. So these are the isomers. You can write the names of the isomers below this. Okay, now fundamental concepts in organic reaction mechanism. What is meant by mechanism of a reaction? Mechanism of a reaction. Mechanism, it is the sequence of elemental steps. It is the sequence of elemental steps describing details of electron movement, energetics, bond cleavage and bond formation, rates of transformation of reactants into products. All these things are included in reaction mechanism. Sequential representation of elementary steps means a reaction will take place in several steps. So there is a particular sequence to take place these steps. And finally, we will reach in the final product. So actually there will be 2 reactants and there will be final products. We can represent in a single step, but even then it may pass through different elementary steps. First, reactants may combine to give an intermediate. That intermediate may decompose to give the products. So there will be different elementary steps, and the arrangement of these elementary steps in the correct order, that is the sequential representation of each step. A sequential representation of each step describing details of electron movement, energetics during bond cleavage and bond formation, and the rate of transformation of reactants into products is referred to as reaction mechanism. In reaction mechanism, first we can see what is meant by fission of a covalent bond, bond cleavage, breaking of a bond, how it is possible, how many types of bond cleavages are present. We can see there are 2 types of bond cleavages. The first one is heterolytic cleavage. Heterolytic cleavage. When a covalent bond breaks, the shared pair of electrons move towards only one of the atom. Then that particular group will become negative and the other group will become positive. The bonds breaks in such a way that the shared pair of electrons remain with one of the fragments. It results in the formation of positive and negative ions. An example, CH3Br. When it dissociates, the bonded pair of electron completely moves to bromine. So bromine changes to Br minus bromide ion. and CH3 changes to CH3 plus methyl ion, methyl cation. We'll call a cation containing carbon atom as carbocation. Species having carbon atom possessing positive charge is called carbocation. Now the another type or the second type is homolytic cleavage. In homolytic cleavage, the bonded pair, in the bonded pair, one electron will go to one of the bonded atom and the other electron will go to the other bonded atom. So equally, the electrons are as it is donated, the electrons will go back to its source. That is homolytic cleavage. Then we will get two species which will be same and without any positive or negative charge, and the two groups will possess an unpaired electron, so we'll call it as free radicals, very reactive free radicals. One of the electrons of the shared pair in a covalent bond goes with each of the bonded atom. It results in the formation of free radicals. Here is an example. Rx means an alkyl halide. R represents alkyl group. CH3, CH3, CH2. All these represented by the letter R. X represents a halogen. Chlorine, bromine, iodine. All these are represented by X. Rx means alkyl halide or haloalkane. When it is subjected to sunlight, what happens? It will break, and that bond cleavage will be a homolytic cleavage. The bonded pair of electrons, one will go to the alkyl halide, one will go to the alkyl group and the other one will go to the halogen. So we will get two free radicals, alkyl free radical and a halogen free radical. Alkyl radicals are classified as primary, secondary or tertiary. Alkyl radical stability increases as we proceed from primary to tertiary. Here you can see CH3 dot, it is a methyl free radical. It is a primary free radical also. Here the one carbon atom is bonded to only, it is not bonded to any other carbon atom, so it is a primary carbon. And the radical is primary free radical. Here CH2, this carbon atom is bonded to one another carbon atom. This one also considered as a primary free radical. Here this carbon atom is bonded to two CH3 groups, two carbon atoms. So it is a secondary carbon free radical. And here this carbon atom is bonded to three other carbon atoms. CH3 thrice means C single bond, CH3 single bond, CH3 single bond, CH3. This bonded to three other carbon atoms. So it is a tertiary free radical. The names are given here: methyl free radical, which is highly unstable; ethyl free radical, unstable but more stable than CH3; isopropyl free radical, unstable but more stable than ethyl free radical; tertibutyl free radical, unstable but more stable than isopropyl free radical. So out of these different free radicals, which is most stable? Tertiary butyl free radical, that is more stable. Okay, now nucleophiles are electrophiles. The attacking reagents are named as nucleophiles and electrophiles. Nucleophiles means nucleus loving. Nucleus loving groups are negatively charged groups or electron rich groups. Electrons always seeking for the positive charge. Nucleus provides the positive charge. So nucleophiles means nucleus loving, means electron rich or negatively charged groups, that is nucleophiles. A reagent that brings an electron pair to the reactive site is called a nucleophile, represented as NO double dot. That represents an electron pair. That is nucleus seeking, and the reaction is then called nucleophilic reaction. It may be nucleophilic substitution. A reagent that takes away an electron pair from a reactive site is called electrophile. Electrophile means electron seeking or electron loving. That will be a positively charged species, therefore it is represented as E plus, electron seeking, and the reaction is called electrophilic reaction. It can be an electrophilic substitution. Here you can see a number of examples for nucleophiles and electrophiles. It is given as a question. Giving justification, categorize the following molecule or ions as nucleophiles or electrophiles. HS minus negatively charged. So it is nucleophile. BF3, electron deficient. It is a Lewis acid. Only 6 electrons in the valence shell of boron. So always it is seeking for electron. So it is an electrophile. C2H5 O negative. There is a negative charge. So it is a nucleophile. CH3 thrice and double dot. It represents an electron pair. So it is a nucleophile, electron rich nucleophile. Cl plus, electrophile, electron seeking. CH3 C plus, double bond O. It is also an electrophile, electron seeking. NH2 minus, nucleophile. NO2 plus, electrophile. That is classified here. HS minus C2H5, O minus C3 thrice and NH2. And electrophiles BF3, Cl plus, CH3 CO plus, NO2 plus. Electron displacement effects in covalent bond. In organic reactions, it is very important. When we discuss the reaction mechanism of organic reactions, you should have a clear idea on this topic, electron displacement effects in covalent bonds. The first one is inductive effect. It is a permanent effect in which there is shifting of electrons through carbon-carbon sigma bond due to the presence of an electron donating or electron withdrawing group in the molecule. It is a permanent effect that is present in the molecule, and that effect is due to an electron donating or electron withdrawing group in the molecule. And what is the effect? It is the shifting of bonded pair of electrons towards any one of the atom through a carbon-carbon sigma bond. An example is given here, CH3, CH2, Cl. Here chlorine is attached to this carbon atom, which is an electron withdrawing group. It will attract the bonded pair of electron towards it. Therefore, it will get a slight negative charge, and this carbon atom will get a slight positive charge. The effect will not end here. This positive charge will attract this bonded pair of electrons. So it will extend through sigma bonds. Therefore, a slight shift. We can expect a slight shift of electron pairs to this carbon atom. As a result, a still smaller positive charge will develop here. Delta positive means a small positive, a very small positive charge. Delta positive means very small positive charge. Very small positive charge will develop here. And if there is a third carbon atom, there also we can see delta positive charge will develop. And beyond the third carbon atom, inductive effect will not exist. That is inductive effect. There are two types of inductive effects, plus I effect and minus I effect. Nitro, NO2 minus, cyano, CN minus, carboxy, COOH, ester, COR, aryloxy, OAR. Example of C6H5, etc. are electron withdrawing groups, and these groups induce minus I effect, negative inductive effect, minus I effect. The carbon chain will get partial positive charges. And the alkyl groups like methyl, ethyl are usually considered as electron donating groups, and these groups induce positive inductive effect or plus I effect. Resonance effect or mesomeric effect. You have studied resonance. What is resonance? If it is difficult to represent the properties, or if it is difficult to explain the properties of a compound with a single structure, we will use several structures to explain the properties, and these structures are known as resonance structures or contributing structures. And the exact structure, which is difficult to represent, that exact structure is known as resonance hybrid All these things we discussed in detail in the 4th chapter. So here we can see what is resonance effect. Resonance effect, also known as mesomeric effect. The resonance effect is defined as the polarity produced in the molecule by the interaction of two bonds or between a bond and lone pair of electrons present on an adjacent atom. The effect is transmitted through the chain. Usually, we can observe it in conjugated systems. In conjugated system, alternate double bond systems, we can observe it. In a simple sense, it is alternate double bond system. Shifting of pi electrons. Resonance effect involves the shifting of pi electrons. Inductive effect, shifting of sigma electrons. But resonance effect, shifting of pi electrons. Pi electrons, shifting of pi electrons to a carbon atom carrying a lone pair, or against, moving away from a carbon atom carrying a lone pair. Lone pair can come to the bond. At that time, the bonded pi electron will shift to another atom. So such a shifting, that is known as resonance effect. The resonance effect is defined as the polarity produced in the molecule by the interaction of two bonds, two double bonds, conjugate double bonds, interaction between two conjugate double bonds, or a bond and lone pair. A lone pair is coming to the carbon atom. We are discussing organic compound, carbon atom to form a double bond. At that time, the double bond already present will break and the pi electrons will move to the next carbon atom. A bond and lone pair of electrons present on adjacent atom. This effect transmitted through the chain, carbon-carbon chain. This effect is transmitted through carbon-carbon chain. Here also there are two types of resonance effect: positive resonance effect and negative resonance effect. Positive resonance effect represented as plus R effect, minus resonance effect represented as minus R effect. In this effect, the transfer of electrons is away from an atom or substituent group attached to the conjugated system. Here you can see when NH2 group is present in benzene ring, electron pair from NH2 group is moving to the benzene ring. Electron pair from NH2 group is moving to the benzene ring. Such effect is known as plus R effect. Here the substituent is getting a positive charge. If the substituent getting positive charge, that is plus R effect, and the ring is getting negative charge, that is plus R effect. So NH2 is donating this electron pair. Then what happens? It forms a new bond here. When it forms a new bond here, this pi electrons cannot remain here. This bond will break and the pi electrons will move towards this carbon atom. That condition is here. NH2 has a plus charge. Here a double bond is formed. This bond is broken, and here a negative charge is there, and it is not possible to keep negative charge here. Suddenly it will try to form a pi bond here. At that time, this pi bond will break and electrons will shift to this position, and it will continue. That is resonance. It is positive resonance effect. Now negative resonance effect. This effect is observed when the transfer of electron is towards the atom or substituent group attached to the conjugated system. For example, in nitrobenzene, this electron displacement can be represented as it is shown here. Nitro group is electron withdrawing group. It will attract electron. It will take this pi electron from benzene ring. When it takes this pi electron from benzene ring, here develops a positive charge. Here it will get a negative charge. So it is known as minus I effect. And in order to neutralize this positive charge, it will take this pi electron. At that time, what happens? This bond will break, this carbon atom will get a positive. That is shown here. And that will continue in this way. There are groups which can give plus R effect. Which are the groups giving plus R effect? Halogen, OH, OR, OCOR, NH2, NHR, NR2, NHCOR. These groups use plus R effect. Or we can call this as activating groups. Minus R effect, COH, CHO, CO, CN, NO2. These are inducing minus R effect. They are also known as deactivating groups. The groups which are giving plus R effect are orthopara-directing, and the groups which are giving minus R effect is meta-directing groups. So it is plus R effect and minus R effect. Okay, today we can stop here. We can discuss the remaining effects in another class.